Okay, welcome back. By now, you're all experts in collider physics. I've given you some idea why we perform these measurements, at least some. Now, let's look a little bit in more detail about on the at the basic physical concepts of the collisions. The idea is that we go through the types of collisions in contemporary particle physics, plus and minus, EP, hadron, and discuss the relevant kinematics and what is measured. The reason for this is that there is a crucial interplay between these different types of collision. Put together, we get precision tests of the standard model that would not be possible individually. So we need to discuss some prerequisites. In principle only special relativity, but you should also know this, and you probably do, but because we will make use of this formulae in various contexts, it is worthwhile if we go through this carefully and reuse it later. I'm sharing my iPad, so I stop sharing here. Projecting now. I think it works. Yes, we have. Start a new. Okay, so let's discuss some basics of special relativity, the kinematics of four momenta, nothing more. We can write the four momentum P mu as in components as E over C and P. The vectorial P is the three components. The three components of the 3D momentum, and we can write this as mass m. If I pull out the mass m, I would write here gamma factor c, and the momentum would be written as eta times gamma times c. I'm essentially only giving you now all the ways in which we can write a relativistic four momentum. So we can continue writing this as m gamma c times 1, and the spatial components would be beta. Now we know that p squared is p mu. Is, if we look at the last way to write that, it would be m squared c squared times gamma squared 1 minus beta squared, and this is 1 because gamma, relativistic gamma factor, is square root of 1 over square root of 1 over 1 minus beta squared. In particular, we can use the first way to write the four momentum, and the last one to derive a formula that we use in a moment, the velocity beta in units of the speed of light is p over e divided by c. So it's just p over e times c. You realize that I did not put the speed of light to 1. We'll do so in a moment. We can also calculate the for momentum invariant mass m squared c squared by looking at the first way again to write it. So this would be e squared over c squared minus p squared, or the famous relation E equals mc squared in our language, m squared, well, this way to write it, including the momentum, m squared c to the 4th plus c squared p squared. Nice. So that's basic relativistic kinematics. Let us now perform a Lorentz transformation. Lorentz transformation we can, for example, write as Lorentz transformed energy and momentum are given by matrix multiplication gamma, beta gamma, beta gamma, gamma. So typically, these components are measured in a system S. This is the Lorentz transformation that gets you from S to S prime. That's a system that moves with respect to S with constant velocity, and these are the components then as measured in the system S prime. P parallel means the component of the momentum parallel to the direction of the relative velocity of system S and S prime. We know that the normal component of the momentum is unchanged. Good. So these are the basics of, these are the formulae how I define the Lorentz transformation. You realize that I already put c equal to 1. Okay. Let us now compute. Let's now do a calculation that we have begun last time. Let's compare. Let's compute the center of mass energy of two colliding particles, for example, in a beam. So we would just we use we simply use the E and P notation, and it's trivial to insert these components. The negative sign is from the Minkowski metric squared, and then we have the square root here. We can write this as, by means of simple rearrangement, we take the squared here, we take minus P1 squared here, then we have P2 squared minus P2 squared here, and then we have here 2 E1, E2 minus 2, and that's a 3-component in product. And then we take the square root. And so now we use, here we use P equals eta times E, which is an equation for every particle that, that holds for every energy particle that we've just derived. So we can write this as, because this is now m1 squared, and this is now m2 squared. So we can write this as m1 squared plus m2 squared plus 2e1, 2. That comes with a factor of 1. That's this term here. And then we have minus beta 1 in beta 2. And that's just beta 1 times beta 2 scalar multiplication times the cosine of the relative angle. No secrets here, I suppose. We specify this to the collision of a particle P1 that's moving. We are now in the rest frame of a fixed target experiment where there is a particle P2 at rest. That means P2 equals M2, and then here 3 zeros. So this equation in the lab frame, let me write it like this, becomes M1 squared plus M2 squared plus 2 E1 as measured in the lab frame times M2. And this is, if we can neglect the masses of the particles P1 and P2, this, the leading term here, is square root of 2 E1 lab times M2, which holds in the lab frame of a fixed target. If we compute this in the center of mass system of two particles colliding, how is it defined? The center of mass system is defined by P1 plus P2 equals 0, which can immediately be used to simplify the equation, because if this term is 0, only the first term survives and becomes E1 plus E2. And E1 and E2 are potentially different only because the masses of this particle are different. The momenta are, the absolute value of the momenta are the same. So if we put M1 to M2, if the mass is equal, this is just 2 times the energy that each of these particles carries in the center of mass, system. So in a fixed target experiment in the lab frame, we get square root of 2 times the energy of the moving particle times the mass of the particle at rest, and in the center of mass system, we get 2 times the energy of the particles that are moving. Let me now unshare and share back the slide, because quantitatively this makes a very big difference in the following example. Yep, I'm sharing again. So I'm projecting now the calculation that we have just done. Take as an example 1 and use your pocket calculator to check these numbers. A beam of kaons, for example, with a mass of roughly 500 MeV, a momentum of 0.8 GeV, and shoot them at the proton target. That's, by the way, a real-life example. At the proton target of with a rest mass of 1 GeV, we very roughly get 1.7 GeV, which means, because these are not ultra-relativistic, ultra-relativistic particles, the beta and the gamma factors aren't extremely high. We more or less get 0.8 plus is 0.9 here. There's rather little loss. So that's a fixed target experiment at lower energies, and the square root, the square root of mass energy that's available to produce new particles, in case you're interested, what is they produce, is not, there's not a lot, there's not much loss here. However, consider a different example. NA48 is an experiment, it's a fixed target experiment at CERN where 450 GeV protons were collided with beryllium nuclei. Beryllium nucleus has a mass of 0.4 GeV. Now, if you take this formula in the lab frame, you will compute 2 times 450 times 8 in the square root is 87. So while you have 450 GeV protons and it costs a lot to accelerate those protons and build a collider, the SPS, to produce those, in a fixed target experiment, you only have around 90 GeV available. If you collide 2 of these protons in counterclockwise motion, you will arrive at almost a TeV, 900 GeV, which in terms of discovery potential is a different league. So please run these numbers and see how in fixed target experiments, the center of mass energy is reduced in ultra-relativistic collisions, which gives you, among many, gives you a feeling for the kinematics of collisions and also gives you the reason why we cannot work at the energy frontier with fixed target experiments. By the way, NA48 produced these collisions, made these collisions to produce kaons and then studied CP violation in the kaon system. And it is a side experiment to the anyway operated SPS, LHC and pre-accelerator, and hence it is not a real financial loss. It just used the available 450 GeV protons from the SPS. Okay, now we talk about experiments. First thing a student should be acquainted with in the experiment is the coordinate system. An example that I know best, here's the LHC tunnel. Here's the CMS experiment, here's the ATLAS experiment, Alice and LHCb. The Z coordinate points in the beam direction to the Mount Jura, in case you can't see it if you're underground, but it points towards the Mount Jura. The X coordinate points inwards and the Y coordinate points upwards. Here is a cross-section of the ATLAS inner detector. In a later lecture, we will discuss what these subdetectors mean. It's a pixel detector, transition radiation tracker, silicon trackers, and so on. You will see here the symbol eta. In principle, one does not need eta. One could use the angle theta that's measured from the y-axis. However, in high-energy physics, we use eta, and eta is minus the logarithm of tangent of theta divided by 2, which may sound like a crazy convention. It is indeed jargon. Eta is called the pseudo rapidity. Eta equals 0 means that theta equals pi. If eta is 0, then theta is pi. So eta equals 0 for example, is the transverse plane to the beam direction. So typically we use eta to identify where in the RC plane we are in terms of subdetector component. For example, the central region of the detector is at low eta. So eta around 0 to 1, this is what we call the central region of the detector. Most of our detectors are cylindrically shaped with end cap discs. So it has a bit of an onion structure. We call the end cap detectors, we label the end cap detectors, which are typical at eta values of 2.5, 2, 2.5, and 3. And then very forward, close to the beam pipe, the eta values are 3 to 5. You can compute, no secret, to compute the theta values for this different pseudo rapidity, but it's not necessary. We should stick to eta for the following reason. And this is again relativistic kinematics. Let me again share and do a calculation with you. So I unshare. We continue rewriting the relativistic form momentum. I share my screen. Start broadcast. We write, as we did before, P. C is speed of flight is put to 1. So the form momentum is just E and P. We had pulled out M gamma. Now let us pull out, instead of M gamma, let's pull out the magnitude of the momentum. Then we would write here square root of 1 plus m squared over p squared, and then we can use spherical coordinates. Which you are familiar with. And absolutely nothing has happened. Maybe note that for m equals 0, it's trivial to show that p squared equals 0 just from the identities of the trigonometric functions. Sine squared x plus cos squared x is 1. Now, you will see in a second why I emphasize this. Let's now pull out the magnitude of the transverse momentum, okay? The magnitude of the transverse momentum is square root of px squared plus py squared. And let me use the following parametrization. So here I write cosine hyperbolicus squared of eta plus m squared over pt squared. And then I write cosine phi, I write sine phi, and I write sine hyperbolicus. Now, if you compute the p squared here, the form momentum, you get pt squared times m squared over pt squared oh, something's wrong. Plus cosine hyperbolicus squared eta minus cosine squared phi minus sine squared phi. And that's 1, and that's minus 1. So that's correct, it's m squared. Which means that this is a good way of parameterizing four momenta of particles of mass m. The question still is, why would anybody do that? Let me show you why anybody would do that, why we would do that. Let us, however, consider a simplified case. Let's now put the mass to 0. If the mass of the particle is 0, we can still have the four momentum written outside, and it simplifies a little bit. If you cosine hyperbolicus eta, cosine phi, sine phi, sine hyperbolicus eta. Good, that's a simplified way of writing the four momentum simplification is that the mass of the particle is 0. Let's now do a Lorentz transformation. And the matrix of the Lorentz transformation in these four dimensions is just gamma, beta gamma, beta gamma, gamma, and two ones in the diagonal because we Lorentz transform in the beam direction, which is the c direction. Let's do it. P prime is the matrix multiplication of the Lorentz transformation matrix with the vector as written here. The transverse momentum doesn't change because of the ones in the middle here, but you only really need to do the matrix multiplication, and it becomes gamma cosine hyperbolicus eta plus beta gamma sine hyperbolicus eta, and then, as we said, the transverse direction doesn't change, but the c component, of course, changes. And now let's compute eta prime. What is it? So the question is this quantity eta, which is a simple function of the angle theta, how does it Lorentz transform? And I'm going to compute the tangent hyperbolicus of eta prime, because that's easy to compute. It's the last component divided by the first component of the Lorentz transformed four vectors. So it is again the last component divided by the first component. And we see that the factor gamma immediately cancels out because it appears everywhere. So I do not write it. Instead, I write here the last line without the gamma is beta times cosine eta plus sine eta divided by the first line, which is cosine eta plus beta sine hyperbolicus eta. And now I divide by sine hyperbolicus eta. I'm sorry, I divide by cosine hyperbolicus eta in the numerator and in the denominator, and I find beta plus tangent hyperbolicus eta divided by 1 plus beta tangent hyperbolicus eta. If you look at this formula, it's x plus y divided by 1 plus x times y. It probably reminds you of relativistic addition of velocities, and that's exactly what's happening. So let's do a trick as usual in special relativity. We write the beta as tangent hyperbolicus of tangent hyperbolicus inverse of beta. That's just beta plus tangent hyperbolicus of eta divided by 1 plus, so there's a parenthesis here, tangent hyperbolicus of hyperbolicus inverse beta times tangent hyperbolicus of eta. And now you need to know that, I write it here, that there is an addition theorem for the tangent hyperbolicus. This is just tangent hyperbolicus of x plus y. And we can use it here. And this becomes, therefore, tangent hyperbolicus of eta plus tangent hyperbolicus inverse of beta. And therefore, eta prime is eta plus tangent hyperbolicus inverse of beta. And this has far-reaching, this formulation has many advantages. In particular, it means if we have our detector, let me draw it here, and we have an event, say here are particles in a jet and here are particles in a jet, this is the z direction, then we can Lorentz transform this event. It would look like this. There would be particles here and there would be particles here. So if this was at pseudo rapidity 0, this here would be at the pseudo rapidity of tangent hyperbolicus inverse of the speed I boosted with. And the crucial point is that delta eta is independent of eta, because delta eta is just this inverse tangent hyperbolicus of the speed I'm boosting with. Because delta eta is independent of eta, we know what happens to the particles in an event if they get a Lorentz transformation along the z direction. Namely, they are each shifted by the same amount. Why is it important? Because with, for example, proton-proton collisions, I have a proton going in this direction, I have a proton going in this direction. Let's assume something interesting happens. I don't know what it is, but it is the collision of two gluons. The gluons carry a fraction x of my first proton, and this is the first gluon, and this second gluon carries a fraction x2 of my second proton. And I don't know the numbers x1 and x2. So maybe here, what could have been produced? Maybe a Higgs boson has been produced. That's certainly possible if two gluons collide. So I know that the square root of the square root of s of my gluons. Let me write this more carefully. the square root of S of my gluons is certainly greater than the Higgs mass. Okay, that I know because I've produced the Higgs boson. But I do not know, for example, whether X1 was greater than X2 or whether X2 was greater than X1. In my decay products of the top of the Higgs boson, for example, the two photons, they could be, in one case, emitted. If I draw my detector here, I have my collision happening here. In one case, they could be in the transverse plane, so that would be photon 1, and that would be photon 2. And in the next event, the role of X2 and X1 are completely different. For example, at one point, X1 could be big. This could be the proton that's coming from the left. X1 is big, and X2 is a much smaller momentum. In this case, the photons would be emitted in this direction. They would be boosted towards the more forward momentum, towards the more forward detector component. But I know that the angular difference between the angular difference that's induced by the boost, so the amount in the lab frame by which the particle is boosted is constant if I use eta. For example, let's say delta eta equals to 1, and I'm actually almost, delta eta is equal to 1, then each particle moves from the eta value it has to the eta value plus 1. Without doing complicated Lorentz transformations. So by using the pseudo rapidity, we have a detector, we can define a location in the detector that is very easy, that behaves in a straightforward way with Lorentz transformation. If you think of the transformation of the angle theta, you have to go back to the synchrotron radiation chapter where we did the similar calculation for that, and it's much more complicated. In particular, delta theta does indeed depend on theta. It's not a constant shift. So for the pseudo rapidity, we have a constant shift. And let me give you another reason why this is important. Let's assume you want to define the closeness of two particles. So you have a particle 1 and a particle 2. You can define an angular difference that we conventionally call delta R and define it as a delta eta squared plus delta phi squared. The point is now that delta R prime is delta R, because the delta eta is Lorentz invariant with respect to Lorentz transformations in the C direction. Okay, this is because every particle, as we said, receives a constant shift in the pseudo rapidity, which is tangent hyperbolicus inverse of the speed that it's transformed with. So the difference is Lorentz invariant. Let me use my red pen to highlight this. It is delta R prime is delta R because delta eta prime is delta eta for boosts along the C direction. So we have an angular measurement that's Lorentz invariant. Why do we have why is it really an angular measurement? There's something to show here. You can do a Taylor expansion. I still write in red. If you do a Taylor expansion, you find that theta equals pi half minus eta plus terms of the order eta cubed. So only by changing the variable, we can save us a lot of work. Let me unshare now. Let me this calculation is certainly worthwhile to do on your own. It's also simple. Oops. And it's in the slides. So the point is, if we have now, let's look again at our detector slice. If we have a particle that's at eta of 1, if we Lorentz transform to a different, if we Lorentz transform the event, so if we consider an event that's boosted, that's moving along the z direction, which we have to, because it's protons colliding, and we are not in the center of mass frame of the colliding constituents, which are the quarks and the gluons. So by boosting from the center of mass frame of, let's say, the quark rest frame to the lab frame, every decay particle gets a constant shift in eta. And differences, therefore, are unchanged. That's why pseudo-rapidity is really preferable, and you will often find phrases like high eta, low eta when discussing the kinematics of particles in the end product of collisions in collider experiments. Good. There was one topic. The second topic is more simple. That's a little bit of a home exercise. It takes exactly 5 minutes to carry out. It's the Mandelstam variables. Oftentimes we have most of the times we have 2-to-2 collisions. That means a particle 1 collides, for example, with a particle 2. We mention here that time evolves from left to right. So particle 1 collides here. In this case, it's written as an antiparticle. The particle 2 produces something intermediate, and then this system decays into P3 plus P4. The relevant momentum invariant of the system during this type of interaction is S, is just the sum of the momenta, P1 plus P2. We could also have therefore we call this the S-channel interaction. There is also the T-channel interaction, which has its name from the T shape here in this diagrammatic depiction. You assume that for example, a proton from the left comes, a proton from the right, and they exchange a photon because they are both charged. That's possible. So they interact. This would be a T-channel interaction. The momentum here in the middle is therefore called T, and it is the difference of P1 minus P3, because at each vertex, the momentum has to be conserved. So the Lorentz invariant T is P1 minus P3, which is at the same time P2 minus P4 squared. And then something that is not used usually is you can also flip the outgoing particles, and then the third Lorentz invariant would be P1 minus P4. So with two four momenta with two particle four momenta, we can define these three Lorentz invariants. Now, I added it here. So that was the prerequisites. Now let's look at the important types of collisions. That's an overview. We have electrons. We have E plus E minus collisions. E plus E minus collisions because electrons are particles that are easily accelerated. Positrons are easily created, and despite the collider limitation is the synchrotron radiation, but other than that, these are very convenient particles to accelerate and collide. The reason is that they are not composite. As we've discussed, if you fix the beam energy, you can immediately compute the center of mass energy of the collision, and then see if the energy is high enough, what new phenomena appear in the collider, the events that are reconstructed and analyzed. Because the square root of S is really only driven by the beam energy, as if you have to scan the energy if you do not know where to look for a new particle, for example. Good. So E plus, E minus are therefore a very clean probe of the standard model, as they are elementary particles. Now, next we could do electron-hadron collisions. And hadron, let's say a proton. High energetic collisions mean that in the lab frame, the proton is Lorentz contracted along the direction of its movement. For example, the protons in the LHC have a gamma factor of 6,500 currently. That means they have a diameter of 1 Fermi and a width in the lab frame of only 1/6000th of a Fermi. So they are actually extremely thin Lorentz contracted disks. We can imagine that we collide highly energetic protons, for example, that has happened at Hera, as we've discussed before, and collide them with electrons. Now that means we have an electromagnetic interacting probe, the electron, that can penetrate the proton and interact with the quarks and whatever we may find, but mostly the quarks, inside, according to the standard model, it's only the quarks, inside the proton, and reconstruct all the particles that are created in this potentially violent reaction. In other words, electron-proton collisions probe the internal structure of the hadron. Once we know the internal structure of the hadron, the proton, we can collide two protons, and from our knowledge of the composition of the proton in terms of quarks and gluons, we can then make predictions for proton-proton interactions. So the big picture in this part of the lecture, the big picture I want to give is that precision tests of the standard model are often easiest done in E plus E minus collisions because you do not depend on the complicated structure of the proton. These hadron-hadron interactions, because the constituent, in each event, the constituents pick up a different fraction of the initial momentum of the parent proton, these collisions probe a wide energy range of for example, quark-quark collisions or quark-gluon collisions. But in order to know what's inside the proton, we have to have an intermediate step of electron-proton collisions that really help us understanding we're going to discuss this in terms of deep inelastic scattering, that help us understand the structure and the content of the proton. So all three together are required for precision tests of the standard model. Then, of course, there are other types of collisions that involve ions. One can shoot electrons at ions to see whether there's any difference in the distribution of the quarks because of the bound state nature of the ion in terms of nuclei. One can shoot protons at ions and one can shoot ions at ions. If one does that, these are called heavy ion collisions. If these are large-scale system, then the focus of the study is less on the fundamental interactions, so on the interactions of, the focus is less on the interactions of the quarks and the gluons, but rather on the collective behavior. So here I try to depict Lorentz contracted heavy ions. One comes from the left, the other one comes from the right. There will be, in each collision, there will be a certain degree of overlap, and then happens in the rest frame of the collision, a really violent interaction with an immense number of particles reacting at the same time. And the assumption is that the quarks and the gluons form a plasma. And indeed, there are hints from experiment, from these high energy collisions, that a quark gluon plasma has already formed in heavy ion collisions at the LHC. So this is a new form of matter. But it is not new in the sense of new fundamental interactions that would invalidate or confirm the standard model. Here we study collective phenomena to learn something about matter in its most extreme form at extreme temperatures that are very close to the these are temperatures that are otherwise in nature achieved, but achieved only very shortly after the Big Bang. So one hopes to learn something about these the behavior of matter at extreme temperatures. So these are the types of collisions that we want to discuss. We start with electron-positron collisions. Now, it's a little bit ungrateful to discuss this because I cannot do with you all the theory calculations. You have, as I said, theory lectures. Nevertheless, it's useful to know a few basics. It's also important to understand a few, very few, key features of E plus E minus collisions, because they will come back when we study detector physics. Because after all, the interaction of a particle with a detector material is also covered by the standard model. It's just a different energy regime, but it's particle physics at the end of the day. So we need to learn a few things about it. Therefore, if we think back at our overview, we now start with E plus E minus collision. Next, probably not today, but next time we discuss inelastic scattering and how it is used to derive predictions for hadron-hadron collisions. I'm not at all an expert on heavy ion collisions, so I will not focus on that. Good. So the scattering amplitudes of reactions of elementary particles are represented by so-called Feynman diagrams. This is perturbation theory in a very similar sense as you've learned it in quantum mechanics. So in quantum mechanics, one has an interacting Hamiltonian that transforms an initial state into a final state. The Feynman diagram can be seen very similarly. One has an initial state of two particles, then one has an interaction Hamiltonian that accounts for the interactions of these particles. New particles can be created or absorbed, and eventually into a final state. And to improve the perturbative precision, more diagrams and more complicated diagrams have to be drawn. Feynman in the 1930s invented this technique to organize the calculations of quantum electrodynamics. And the rules are really simple. I only give you an example. As I said, I cannot do the calculations at the Technical University. This is taught in Atomkern- und Teilchenphysik 2. I know that Axel Axel Maas is teaching this. He's teaching perturbative quantum field theory courses as well. So we have, for example, two electrons colliding. They annihilate, produce a photon. I've already told you this diagram is called the S channel. Time goes from left to right. So the momentum here is P1 plus the relevant momentum in this process is P1 plus P2 squared. And then two fermions may be produced. I call them F here because I don't yet want to specify what fermions these are. You can think of electrons could also be muons. The Feynman rules tell you that for each object in this diagram, you have to write a certain expression, and then you have to multiply all these expressions. For example, for the initial state electrons and for the final state fermions, you have to write this. You have to write spinor expressions. For each of these vertices here, where the photon couples at the fermion, you have to write this what's called a gamma matrix. And for the wiggly line, which represents the photon connecting the two interactions, you have to write what is called a photon propagator. And the photon propagator is the Minkowski metric G mu nu, which connects the two gamma matrices, divided by the momentum of the photon, which in this case would be simply S. The rules further state that you have to draw all the diagrams that are possible and sum them up. And this then gives you a matrix element. So this is the matrix element is then a complicated expression as a function of the ingoing momenta, the charges that appear here, gamma matrices, and metric tensors appear. So they all have to be multiplied. What does this look like? In principle, you have to, well, not in principle, in truth, you have to add up all diagrams that you can draw. So that's the S-channel diagram. Electron-electron goes to fermion-fermion. Let's see, if the fermion was an electron, you also have the T-channel diagram. So the electron just exchanges with the positron a photon. This is not possible. This is not possible if the electron, if the fermion here was a muon, then the T-channel diagram would not contribute, because in the standard model, there is no vertex that would change an electron into a muon by exchanging a photon. That's not possible. And therefore, it depends on what this fermion is, whether you need to add this second diagram or not. Whatever it is, you need to draw all the combinations and add them up. Once you have done that, one can compute the differential cross-section. We know already what a cross-section is. It is in terms of, it has a unit of barn is our conventional unit. The differential cross-section is just the cross-section in bins or as a function of the kinematic observables of, for example, the input or the final state particles. So the differential cross-section is the number of interactions per unit time per target particle in this definition and per incident flux. The general structure of this of the differential cross-section of a 2-to-2 process comes from scattering theory and is given here. So differentially, the differential cross-section d sigma has a flux factor, which is, remember when we calculated the luminosity, we had a factor 2 times delta relative velocity of the two particles. This here is the relativistic form of the reciprocal value of 1 over 1 over the velocity difference of the initial state particles in a relativistic form. It is pretty hard to see here. Also, we are not going to use it, so there is a prefactor. And then, as it is always the case in quantum mechanics, matrix element squared. Then we have momentum conservation, and finally the Lorentz invariant phase space. So differentially D3P and D3P3 and D3P4 of the outgoing momentum. So in principle, I've given you everything. You can take this D sigma, use the Feynman rules from the previous slides that are given here, multiply everything, and compute the differential cross-section of E plus E minus into, for example, another E plus E minus pair. And you make precision, in this way, you will make precision predictions for electron-positron scattering at the collider. I completely understand, and I'm sure you also understand, that it takes a long time to study the details that I've skipped over here. I briefly stop now. Can you, because I want to ask you, who of you is has taken a quantum field theory courses? We're not going to need it and not going to use it, but I would like to know. Do you come from theory? Yeah, Fabian, I see you are unmuted.
Well, I visited a quantum field theory course, and now I'm in quantum field theory too. Okay, so in principle, you, okay, I mean, this probably, do you do renormalization? Do you go at this length, or is it leading, or are these mostly leading order calculations? Yep. Okay, maybe it doesn't, maybe it depends a bit on the topic. Sometimes we also looked at next to leading order, but I think mainly it is leading order.
Okay, but the answer, the real answer is that you know what I'm talking about. That was a question. So very well. I hear that many of you have taken courses in theoretical physics that go through this material in more detail. Maybe the formula is not important. That I've written here. What I've written, what is important here is that in this formula, everything is completely determined. There are no unknown distributions of contents of a quark and a proton somewhere that need to be measured in the experiment. It's really bread and butter physics, and you can evaluate these quantities with a little bit of extra information on how to manipulate gamma matrices, on how to work with this Minkowski matrix, and how to perform this integral, because you appear delta functions and so on. But in this, along these lines, there, except for the fact that it's a lot of work, everything is completely determined and gives you an exact answer without resorting to a large class of other measurements. That's to say, E plus E minus collisions are theoretically very clean. Students can do these simple calculations. Later in life, you can do more complicated calculations and use models beyond the standard model to predict effects at the plus E minus collider that deviate from the standard model, and maybe in a few years we can search for these at CLIC or at FCC-EE. It's not a dirty game. Let's look at, it's a clean game. Let's look at how clean it is. I've talked some we've talked a few times about the Large Electron Positron Collider, LEP, and here I present some results from the Z pole mass, which is the lab run at center of mass energies that are close to the C mass. The C mass is around 91 GeV, and between the years 89 and 95, lab ran at different beam energies, different center of mass energies, very close to the C mass. I give you here the energy ranges that were traced, and here the integrated luminosity. Below here you see a typical Delphi was one of the colliders. That's a typical event display. It's extremely clean. There's very little activity. You see here two back-to-back, probably electrons, two back-to-back particles that are reconstructed in the detector, nothing else. At the LHC in a Hadron Collider, we have 600 to 700 particles, depending a little bit on which year we look, but several hundreds of particles at least in each collision. So, as I've said it many times, but saying it again, because the electrons are fundamental particles, square root of S is given by the beam energy. In order to investigate now the energy dependent effects in the standard model, you have to scan the beam energy, and that takes a lot of time. The C mass scan took 6 years. At the LHC, the scan of the C mass, there is no scan. The protons are the particles accelerated, the constituents collide, and collisions happen at every collision happens at a different center of mass energy, and hence the energy dependence is traced out. At lab that had to be scanned. Let's make it concrete. E plus, E minus going into 2 fermions, and now I pick muons, okay? Now I pick muons. If we look at, for the muons, only this diagram will contribute, and according to the Feynman rules, this gives a Breit-Wigner shape, which is 1 over beam energy minus C mass squared plus the width of the C boson. So the width of the C boson is how wide this peak around the C mass actually is. Why is this an important quantity? It's an important quantity because the width of the C mass can be computed with such Feynman rules and with such Feynman diagrams and integrations, and it receives contributions from all final states. So the C boson, as it is produced in E plus, E minus, can decay to electrons, it can decay to muons, it can decay to tau leptons, it can decay to hadrons, it can also decay to neutrinos. And here's why this is interesting. Because the width of the C boson depends on the number of neutrinos in the standard model. But neutrinos are weakly interacting particles, so you do not know how many neutrino families there are in the standard model. It is predicted, if we go back to our initial slide, very beginning. The standard model contains 3 neutrino families, but how do you test this? And at lab, the number of neutrino families in the standard model could be put to a stringent test by considering the width of the C boson. So the width of the C boson gets a contribution from the neutrinos multiplied with the number of neutrino families. And this can be compared to experiments. So here you see in dots the measurements, and you can do the calculation with 2 neutrino families, with 3 neutrino families, and with 4 neutrino families. And as you can see, this energy scan very clearly reveal that the data is only consistent with the prediction for the case of 3 neutrino families. And that is a very, beside lab has many results, but this is a very important precision result that is still very much used today in neutrino phenomenology. We know for sure that there is no 4th neutrino below half of the C boson mass, because it must be allowed to decay. There is no 4th neutrino below half the C boson mass that interacts weakly as the other neutrinos do. This is excluded by experiment, and it's a bit of a miracle because you do not see these neutrinos, and still you can exclude them. Also, the 3 generations that are indeed in the standard model, none of these events was ever observed. It's an indirect measurement of the total of the width of the C boson. So there was one example at lab. Many more things could be measured. The C boson mass value was measured to very high precision. If you look at the x-axis here, it's 91.185 or 19. So there is a 10 to the minus 3 or so, 10 to the minus 4, 10 to the minus 3 precision on the C boson mass. Also, the W boson mass could be measured very accurately. It is still competing with the world best precision. The results I'm showing here, they are from lab, so they are slightly old, but the LHC precision on the W mass, I think from Atlas, has very recently gone into this regime. For CMS, there isn't even a public result yet. In other words, at the hadron, measuring the W mass at the Hadron Collider is very difficult because of the large event activity, because the plus and minus events are so clean. This measurement of the W mass could be done with extreme high precision. This is a treasure trove that we have for the standard model. Many measurements have been done, redundant measurements that freeze all properties of the standard model to very high precision. For example, the coupling of the C to the bottom and the C quarks is something we exploit every day at the LHC. The forward and backward asymmetries that standard model predicts that the events are symmetric if you exchange electrons and positrons. This has been tested to very high accuracy. Production of 2 W bosons or production of 2 Z bosons. You see here a result, one of the famous plots from lab. This here is the C peak. Here we go to the highest energies. When we calculated the synchrotron radiation, the highest beam energy we considered was 104.5 GeV. That means the center of mass energy is 2 times that. So we go to roughly 210 in square root of S. This is the highest energy that we could achieve at lab. Here it was cut off with synchrotron radiation, but we have beautiful measurements of, I think, these are dielectrons, of 2 electrons, of, here for example, of 2 Ws, and here even of 2 C bosons. They even tried the Higgs boson. The Higgs boson, under this, they didn't know where it was. They at 114 GeV would have been below here. It was not seen, but all mass values below 114 GeV were excluded. So even a lot of our knowledge on the Higgs boson pre-LHC came from lab. It was excluded below 140 GeV. It was not far away. I mean, we now know it's 125. So they were unlucky in a sense. On the other hand, we found it now at the LHC, so I think we were lucky. But if you they could not have gone to 125 GeV. If you go back to the synchrotron radiation, an invariant mass of 125, besides the fact that the Higgs only couples feebly to the electrons, it could not have been maybe discovered, but could not have been studied, would not be possible because the beams would lose their energy so quickly that you cannot have a feasible duty cycle. Okay, I will only speak a one more minute. There are more results here from lab at the C pole. We already had the mass of the C boson with very high precision, the width of the C boson, that third line here, it constrains the family of neutrinos. Here are asymmetry measurements, forward, backward, asymmetry, the mass of the W, and other quantities. Good. The first topic next time is deep inelastic scattering. We are going to discuss what happens when an electron hits a proton, first with a very long wavelength so that it sees the proton as a point particle. Then when we increase the energy, reduce the wavelength so the proton appears a little bit bigger, or when the energy is so high that we can resolve the quarks inside the proton structure, or when the energy is so high that we really can have a precision understanding of the inner workings of the proton. This topic is deep inelastic scattering. It is the second type of collisions I want to discuss. The third one is proton-proton collisions. The first one is already behind us. This was E plus E minus. And that's it for today. Do you have any questions? I know that I did not check. Is there anything immediate you want to ask? Next time we'll make a question session again at the beginning. You can also send me emails as usual. If not, I wish you a nice weekend. And we meet next week. I'll send an email. Okay? I hope you could hear me.
Yes, we did. Okay.
Okay. Have a nice weekend, guys.
Bye.
Goodbye.
Thanks, bye.
Bye.